let's continue with the verb divergence problem. Remember that the threads in the verb are physically related to each other. And in verb, when executing the if-else structure, a verb executes it as single instructions. So we face a similar problem here. The problem is if the threads in the verb execute the different paths of if-else instruction, the execution of if-else instruction becomes serial. What I mean here, if you use thread ID here and get its modular with 2, the threads with even global thread ID executes the if path. The threads with odd global thread ID executes the else path in a verb. So this operations becomes serial. How we can overcome this problem? We must force the threads in the verb execute the same path of if-else instruction. How we can ensure this one? If we use verb ID rather than global thread ID here, we can obtain the verb ID by dividing the thread ID to 32. 32 is the number of threads in the verb. So if we divide the ID with 32, we will get the ID of verb. And if we get its modular with 2, all the threads in the verb execute the if path, or all the threads in the verb execute the else path, depending on the verb ID. So with this approach, we can avoid verb divergence problem. There is an example here. We have two Cuda kernel. The first one is related to the no divergence of case. Here, the second one is the case about the divergence of the threads in the verb. Let's examine the first one. Here, we use verb ID. We have 4 cases here. We use if as structure. It has 4 cases, 4 conditions, 4 cases. And we execute this one inside the for loop. And if you see that here, we use verb ID here, not the thread ID. That means the threads in the first verb performs addition. The threads in the second verb performs subtraction here. The threads in the third verb performs multiplication, and the threads in the fourth verb performs division, and that is also same for the remaining verbs. In the second kernel, we use global thread ID. So that means the first thread in a verb performs addition, the second thread in a verb performs subtraction, the third thread in a verb performs multiplication, and the fourth thread in a verb performs division. As you see, so that occurs a divergence problem in this kernel.
Dear professor, we don't have your voice.
Sorry. Can you hear me?
Yes. Yes, we can hear you.
Okay. And continue. Okay. Okay, now we will execute this one, and the obtain the profiler result, which is related to the work divergence. And the number of data is 2/22 again. There is no non-coalesced access to the global memory in this example. So only the work divergence problem dominates the execution time. Execution time, so oops. Okay, now we obtain the results of profiler. First, let's check the execution time of the kernels. The work node divergence kernel takes around 0.01 seconds, and the execution time of work divergence kernel is around 0.03, and we achieve 3x speed up with work node divergence kernel. And if we check the results of provider, there's a metric about it. It is work execution efficiency metric. And this gives us the ratio of the average active threads per work to the maximum number of threads per work supported on a multiprocessor, and it is expressed as percentage. That means here in the work now divergence kernel, the result is 100 because there is no any divergence, as you see that. So at each running of work, only the one of the path of if as is executed. So all of the threads in the work execute that instruction at the same time. Because of that, at each execution of the works, all of the threads are active. So we get 100% here. But in the work execution efficiency, in the work, this is an average values, remember. The work executes the if as a structure, 1/3 of the threads are executed instructions at a time. This gives us the 34% means in average, 1/3 of the threads are executed the same instruction at a time. And this is what we expect. We expect that the result is 100%. Let's continue with Cuda streams. Our last issue today. I would like to give a definition for task parallelism. Task parallelism is related with the execution of the different tasks over the same data on different processors at the same time. This is what the task parallelism is. And the data parallelism is related with the execution of the same task over the different parts of the data at the same time. This is data parallelism. Data parallelism is the behavior of Cuda, but we can also achieve task parallelism in Cuda by using Cuda streams. Cuda stream executes the instruction in the same stream serially. It is first input, first output manner. I would like to give some explanation about Cuda stream. The instruction in a Cuda stream can be executed with the instruction in another Cuda stream at the same time. If you create more than one Cuda streams, we can overlap the different instructions and we can execute them at the same time. but there are some notes here. When transferring data, only one stream can perform copy post operation in any direction at the same time. For any direction, only one stream performs copy operation. And at most two copy operations can be performed at a time. One from CPU to GPU, one from GPU to CPU. So this is an exception for memory operations, memory transferring between CPU and GPU. Only one in any direction, only as one stream performs operation. So at the same time, only two stream performs copy operation, one from CPU to GPU, one from GPU to CPU. This is an exception for memory operation, but for the other instructions, we will see there is no exception. And in every Cuda code, there is a default stream. It is stream 0. It is a default stream. We have a default stream, and the execution of the stream, the execution of the instructions of the stream 0 cannot be overlapped with the execution of the instructions of the created streams. We will create streams. We cannot overlap the instruction of default stream with the created streams. Remember our vector addition example yesterday. We copy the input parameter A, and we copy the B to the GPU. Then we perform vector addition on the GPU with Cuda kernel. Then we copy the result to the CPU again. This is the definition of the vector addition example. Cuda MEMS CPI and Cuda kernels are executed serially. There is an implicit barrier between the Cuda operations. But in this example, we can see that when the program transfers a data here, copy A or copy B, GPU becomes idle during this process. And as you see that when the program executes the Cuda kernel, now PCI becomes idle. So this is not a good solution for us. So if you want to improve the execution time of the problem, you can use task parallelism here. How we can do the task parallelism? We use pipeline technique and Cuda streams in order to achieve a task parallelism here. So in order to make pipelining and create many streams, first we need to divide the data into 3 parts. Here we divide A into 3 parts. They are independent of each other. We divide B into 3 parts. And since we divide the data into 3 parts, we must also divide the vector addition operation into 3 parts because they are independent of each other. And to copy the result to the host array, again, we divide the data, the result, into 3 parts. And if we rearrange the orders of these operations here, they are independent of each other. If we rearrange the order of these instructions, we obtain 3 independent vector addition operations here. First one here, for the first part of the data, the second one, the second vector addition is for the second parts of the data, and the third vector addition is related to the third parts of the data, and all of them are executed independently each other. So we can now overlap the memory operations with the Cuda kernel operations. How we can overlap it here? As you see that now, we use pipelining, and we overlap here. We overlap vector addition of first part with the memory copy operation of the second part. At the memory operations in the same parts, they must be still serial. These are must be serial, but the operations with the different parts can be overlap here. We overlap transferring data from GPU to CPU in the first part with vector addition of second part, and transferring data from CPU to GPU for the third part here. Now we overlap them. This can be run at the same time. These instructions can run at the same time. So we can create a stream for each part of the vector addition. We create this first stream for the first part, second stream for the second part, and third stream for the third part. And all of the streams will be executed at the same time, and these operations will be overlapped. So we achieve task parallelism with this approach. I would like to show an example. This is an example for a default stream. Here we have a default stream, which is stream 0, and all of the instructions in the default stream cannot be overlapped. There are implicit barrier between the GPU operations, and we will create new streams, but we mustn't execute the GPU operations in the default stream, because we cannot overlap the instruction of default stream with the new created streams here. And this is the example of Cuda streams here. We have two Cuda, we create two Cuda streams. Before that, I would like to mention that this is not the code of this one, this example. The result, the code of this example will be given in the example problem at the end of this lecture. We will see this problem at the end of the lecture. This is another example. In this example, we have two arrays, one for A, one for B. A is the input parameter to the GPU. B is the output parameter copied from GPU to CPU. And we will overlap the operations here. So we divide the data into two parts in this example. We divide the data into two parts. So we divide A and B into two parts. And we create here two streams. This is a stream array, and with Cuda stream create instruction, we create stream 1 and we create stream 2. Then we make a transfer operation here with Cuda mem CPI asynchronized. In order to assign this instruction to the corresponding stream, here we must put the address of the corresponding stream. Since this is the address of first stream that we created, these operations will run in this first stream. And the first part of A is transferred to the GPU here. And the first part of solution will transfer from GPU to CPU here. In the second stream here, we use here the address of second stream inside the Cuda mem CPI, and here Cuda kernel parameter here, as you see. Stream 0 in Cuda kernel, the parameter of stream 1 in Cuda kernel. Now this kernel is executed for the second part of the data. We send the second part of data to the GPU and we send back the results of the second part of the results, B2, to the CPU here. Since we must use asynchronized version of Cuda operations, otherwise the second stream must wait the first stream to be completed their instructions. So we must use an asynchronized version of Cuda's memcpy. So the host continue immediately with the next instructions here, up to this one. The host continue immediately with the next instructions, and the host waits here until the instructions completed in the first stream, and host waits here until the instructions in the second stream to be completed here. So now the instructions of Cuda streams are overlapped here, and all the instructions in all streams are also continue with the next instructions after Cuda stream synchronized, and the streams are destroyed with this command, and the memory locations are freed. So now we overlap the operations of stream 1 and stream 2 in this example. Let's continue with the multi-GPU. If a GPU can access to the multiple GPUs, multi-GPU solutions can be provided. We can run different Cuda instructions in different GPUs at the same time. We must use this instruction, Cuda set device instruction. So there is a parameter here, which is the ID of the corresponding GPU. When we run this one, corresponding GPU will be active, and the instructions following this instruction will run at corresponding GPU. We can also implement this approach in a multi-GPU. How we can do, I will show it now. We will try to perform that operations on the multiple GPUs. Now, there are some modifications on the example. Let's examine this one. Again, the problem is saying we have two arrays. We divide the data of A and B into two parts. So we will send the operations of these parts to the different GPUs, and we will calculate it at the same time and obtain the results from the corresponding GPUs. Here, now we have a pointer for GPU pointer arrays, and we will allocate memory. We must allocate the memory in the corresponding GPU, in the global memory of the corresponding GPU. So we will try to allocate the A1, the first part of the A1. And this is A1. The second part is A2. First part of B is B1. The first part of B2 is B2. Allocate on the global memory of the corresponding GPU. So at first we set the first GPU, and we set it first GPU. This will be active, and this Cuda malloc operation will be executed on the first GPU, and the second Cuda malloc operation will be executed in the first GPU again. And then we set the second GPU, and we allocate memory on the second GPU with this Cuda malloc for the second part of A. And for the second part of V, we allocate memory on the second GPU. And we will do transferring operation, running kernel, and transferring the results from GPU to CPU. Again, we set the first GPU, it will be active, and we do the Cuda mem operations for the first part of A, and we execute the kernel for the first part of the data, and we send back the result of the kernel from GPU to CPU for the first part of it. And then here, we set the second GPU, and we do the same operations for the second part of the data, but they must execute at the same time. The instructions of the first GPU and the instructions of the second GPU must be overlapped by using asynchronous version of Cuda mem CPI. We ensure this overlapping the instruction of both GPUs. So these operations executed at the same time in two different GPUs. And again, we must synchronize these operations with the host. So we set again the first GPU and use this device synchronize instruction. So host the CPU waits here. When the instructions of first GPU completed, CPU continue with the next instruction. And here we set second GPU and we run the same instruction. So for the second instructions of the second GPU, host waits here. When all of the instructions completed in both GPUs, host continue with the next instructions, which are freeing the memory. So this set device instruction is important for us. We must use it in the proper line, in the proper line of the power code. In our first example, vector addition here, we can also use 3 different GPUs in order to run at the same time. Further, we can also apply a pipelining on each part of the data, on each part of the vector addition. There are 3 parts for vector addition, and for each part, we can also apply pipelining as we learned before. So we obtain additional improvement on the execution time. First, we divide the parts to the 3 GPU, and we apply pipelining on each part on each GPU, and we obtain additional improvement on the execution time. And direct transfers can perform between GPUs. It is peer-to-peer communication, and it is more efficient, and you don't need to transfer data to the CPU. And how we can activate the peer-to-peer addition between 2 GPUs? The most important thing is it is suitable for the hardware. It is suitable for the hardware. We can use Cuda device enable peer access. We will the peer-to-peer becomes active between the calling GPU and the given GPU with the given parameter here. This is the the index of the other GPUs that will be communicate with the calling GPU, and we can disable this peer-to-peer communication by use Cuda device disable peer access. And also we can check whether there is a peer-to-peer communication between two different GPUs by using Cuda device can access peer instruction. And we can copy the data between two GPU by using peer-to-peer communication. We can use Cuda MEMS PI peer instruction. Thank you so much. Now continue with our example problem, vector addition with streams. Now I would like to show you the solution of the example problem yesterday. Then I will tell you the example problem of today's lecture. This is vector addition with streams, and I will show you the solution of this problem. Let's start with the example problem in the previous lecture. This is the problem of yesterday, training of yesterday. We have a vector, we will do vector addition. So the elements on the same index are added and they are stored in the third array. And some of the parts of the solution are missing, and I expected you to solve these operations in the given file. These are memory allocations on the GPU, setting the size of block and size of break on, and copying the data from CPU to GPU, executing the kernel to the kernel, and copying the results from GPU to CPU, and freeing the memory location of GPU and the instruction of the Cuda kernel. Let me show you a solution. Before that, I would like to give you a given file. I would like to show here the places that start with this this character here, add character. They are the missing parts of the solution, and you are expected to complete these missing parts. Here, writing the Cuda code, setting the number of blocks, allocating memory for the GPU, and defining these blocks block size and grid size with the variable, and copying data from CPU to GPU, executing Cuda kernel, copying results from GPU to CPU, and freeing the memory. Let me show you the solution. Here, for the vector addition, there shouldn't be a for loop because all the threads execute this vector addition kernel, and the threads in the world access to the A and B with their global thread ID, and peer-to-peer addition performs here, and the results are stored to the array C. We use if clause. If you remember that in the yesterday, if the size of the array is not the power of 2, sum of power of 32, sorry, some of the threads will try to access to the invalid index of the arrays, and we will face out of bound error. In order to eliminate it, we use if clause here. Okay, we calculate number of blocks with this formula. I told you yesterday. And we allocated memory on the GPU with Cuda malloc. And we copy the array in the CPU to the GPU. And we call vector addition. And we copy the result from GPU to CPU. And we print the total execution time. And in order to check that your kernel is run properly or not, if your solution is true or not, you can check the last element of C, the value of the last element of the C. Right. And we free the memory location on the GPU. That is the solution of vector addition that I gave you yesterday. Now, in the second example, let me show you second one. Now we will use Cuda streams. I taught this example on the previous slides here. Now we are trying to overlap the operations of vector addition kernel into in different streams here. For the first part of the data, for the first part of the vector addition, we create stream 1, we will create. For the second part, we will create stream 2, and for the third part, we will create stream 3. This is the problem, and you will solve the missing parts here. Memory location on the global memory, setting size of block and size of the grid, creating Cuda streams, and the operations in Cuda streams will be overlapped. The operations of Cuda streams will be overlapped. And in each Cuda stream, the corresponding data will be copied from CPU to GPU, and the corresponding Cuda kernel is executed for the corresponding data in the stream, and the result of the corresponding data is copied from GPU to CPU. And you will free the memory location of the GPU. And of course, you must write the instruction of the Cuda kernel. These are the tasks that are given to you to solve this problem. I will show the solution now, but at home you can implement it without checking the solution, and then at the end you can compare your solution with the given solution. Let me show you the file given with the missing parts here. The instructions of the Cuda kernel will be written here. Memory locations will be allocated on the GPU. The size of the block and size of the grid will be declared as DIM3 type. And Cuda streams will be created here. And for each Cuda stream, you will do copying data from CPU to GPU. You will execute the Cuda kernel, and you will copy the results from GPU to CPU. And at the end, you will free the memory location of GPU. Let me show you the solution. Again, the instructions of the vector addition still same with the previous example. And since we divide the data into the 3 parts, now we will have 9 different arrays which will be allocated on the GPU. So we are allocating memory on the GPU for these arrays, for these pointers. And we create 3 different streams here. And we overlap the operations of streams. This is for the first stream. Do not forget to input the address of first stream here. This is the address of first stream. And in my program, you must define the stream here. You must send the stream as parameter to the kernel run. And these are for the second Cuda streams. Don't forget to put their address into the Cuda MEMS API functions and Cuda kernel. And this is for the third stream. Since we use asynchronous version of Cuda MEMS API, asynchronous, remember that asynchronous means host does not wait to complete this operation. Host continue with the next instruction immediately. Since all of these instructions are asynchronous with respect to the CPU, so these are executed immediately by the host, and the host waiting here until all the operations of the events completed. Cuda event record, we start Cuda event record for starting the time. And when we stop the time here, sorry, this one, we can calculate the execution time. And the host waits here until this operation completes. And we calculate the total execution time, and we can check our solution by printing the last value of the array C, and we free the memory locations on the GPU by using Cuda free. And this is the solution of the second example in our training. If you have any questions about the solution or about the issues that I told you in the training, you can ask now. I will give you a couple of minutes to ask any question. I'm waiting for questions.
Okay, we don't have any question. I think the training is over. Thank you so much, dear Ozcan Hocam, for your excellent lecture, and also thank our valuable participants. And have a good day. Goodbye.
I also want to thank for the participants and for the supporting their exam and their side.
So we
it was a good event for us.
we would like to thank Özcan Hoca for the contribution, and I guess we can end the training now. Then see you at the next event. Bye.
Thank you.
Thank you.